Welcome to this Friday's ICANN-X Talks. My name is Nima. I come from School of Physics, Peking University. I will chair today's ICANN-X Talks. So this is the ICANN-X Talks of the July. The topic of July is a cost nano divide. So today we are very glad we have Professor Ming Qiu from Westlake University will giving invited talk at today's ICANN-X Talks. We also have two panelists, Professor Wei Li and Professor Rong Chen, and an ex-challenger, Julia. So first, please let me introduce Professor Ming Qiu from Westlake University. Professor Ming Qiu received his bachelor degree in physics in 1995 and a PhD degree in condensed matter physics in 1990, both from Zhejiang University. He received his second PhD in electromagnetic theory from the Royal Institute of Technology, Sweden, in 2001. He joined the Royal Institute of Technology as an assistant professor in 2001, then became an associate professor in 2005. And a full professor in 2009. He then joined Zhejiang University in 2010 as a distinguished professor, where he served as the director of the State Key Laboratory of Modern Optical Instrumentation, Zhejiang University. Since 2018, he has been the chair professor of photonics and the vice president for research, Westlake University, China. Professor Ming Qiu is currently editor-in-chief of Photonics X, a topic editor of Light Science and Applications, and an associate editor of Science Bulletin. He leads a number of prestigious grants in Sweden and China. His current research focuses on micro and nano optoelectronics. To honor his contributions to nanophotonic devices, Professor Qiu was elected to the Director at Large on the Board of Directors of Optical and a Fellow of the SPIE, IEEE, and the COS. He also received the prestigious National Science Fund for Distinguished Young Scholars. So today it's our great honor to have Professor Ming Qiu to give us a talk entitled Photon-based and electron-based nanofabrication technologies. Let's welcome Professor Ming Qiu.
Thank you. Thank you, Professor Ma, for the introduction. So now I will try to share my screen. I hope everyone can see my presentation. Yes. Okay.
You see very well. Thank you.
So thank you very much, Professor Ma, for the introduction, and also thank Professor Zhang very much for inviting me to give a talk in ICANN. And ICANN is truly a wonderful seminar series. There are lots of participants, and I'm really happy to exchange some ideas and also share some of our recent work on nanofabrications and how these nanofabrications, new technologies can be applied to optoelectronic devices. So I will give a very short introduction on the background, why we do this. And then we are talking about some trend in optoelectronic devices. And this is also important as the background. So we all know that the global semiconductor market is huge. For 2020, the global semiconductor product even was a little bit affected by COVID-19. But it still have $400 billion market size. And there are lots of the integrated circuits and optoelectronics. While how you can make this integrated circuits, optoelectronic devices, you have to have semiconductor equipments which provide nanofabrications. And that basically is another huge market, accounts for $100 billion US dollars. So this also means that nanofabrication is very important. It's a fundamental set for semiconductor series. But while fabrication of semiconductor device is not so easy, you have to start from, silicon crystals. Let me see if I can start to have my pen. Yes, great. So you have to start from, if I'm talking about silicon-based electronic devices or photonic device, you have to start with silicon. You have to polish, to cut it into wafer, polish them, and then do different devices. You have to do photolithography or sometimes electron lithography. And then you polish them and so on and so on. So actually, many of such steps I'm not going to explain here. Many of you know, but they repeat themselves. So it seems like only 10 steps. Actually, it's hundreds or even sometimes thousands of steps. And then after making them, you slice them, you make optoelectronic device. So it's basically a process from materials to structure to packaging. And this all involve nanofabrications. And in my group, we are mostly focusing on, for the nanofabrication part, is the lithography part. And then actually it's very difficult to do this kind of lithography because it's already approaching the physical limit. And this is Moore's law, everyone knows. And in 2020, TSMC has already realized or approaching 5 nanometer processing lines. And this is, that means 3 1 nanometers are also on the way. And this is in the world of electronics. But for me, I'm basically a scientist, have been working in the field of photonics for more than 25 years. And then we all think, okay, what kind of things we can do in the photonics world? And unfortunately or fortunately, in the world of photonics, we have a diffraction limit. And that means most of photonic device, the minimal size is roughly half of wavelengths. So that means for optical wavelengths, so basically the feature size is roughly around 100 nanometer. Depends on the refractive index. If you have high refractive index, you have smaller size, of course. So then for photonics, in particular, for the optoelectronic device, you have 3 very much different characteristics as compared to electronic device. It involves multi-materials. For silicon electronics, it's basically based on silicon and then other metals involved. But in optoelectronics, there's a trend of merging different 2D materials, organic semiconductors, traditional silicon, 3-5 metals, and many of them. And metals are not wires anymore in this case. They will be photonic devices. And another thing is in future, there will be 3-dimensional devices. Planned manufacturing process will be expanded into space. So this is also a different story. Another thing is that's because you have multi-materials, you have 3-dimensional devices, so you have to do hybrid. So that means you have photonic device, you have electronic device, you have microwave devices, and many of them you may fabricate or manufacture them differently, but you have to integrate them together. And that also involved very complicated hybrid integration. So it's not so easy to solve these problems easily, but we are trying to do something, at least for some of the part. So in my group, in this talk, I will mostly talking about photon and electron-based nanofabrication technology. I will mention two things. One is ice-assisted electron beam lithography and its instrument we develop. And we call this, as a simplified way, is called ice lithography. And then after about 20 minutes, I will talk about the femtosecond laser fabrication and applications. And this is another possible way using photons instead of electrons to make a structure in currently in 2D. We are also looking at the 3D, how you utilize femtosecond laser to make interesting devices. And then I will say a few words on challenge and opportunity. And this is my group. So we have roughly 30 researchers and students in my group. And we are doing many aspects of the photonics, and we are also doing instrumentations for nanotechnology. So this is our lab, and we have a very nice name called Paint. And also very interestingly, I will talk about some paintings in this talk in the next 50 minutes. And in my group, we are doing, as I said, fabrication technologies, but we are not only doing this. And we are doing optoelectronic devices based on this fabrication technology and utilize these optoelectronic devices to do smart applications. We are even doing, for example, AR and VR, and also doing lighting and other interesting applications. But we are focusing this part in today's talk. And this is a very selected publications and results from my group over last roughly 20 years. So we are working lots of things on, we're mostly working on micro nano optoelectronic devices and related theory, fabrication, design, and devices. So we are more working on how the photon and electrons, they will interact with each other, and the mechanism and the technique and device behind it. But there are too many things to describe in this. I don't have enough time. Professor Zhang and Professor Ma only gave me 1 hour, so I would like to select the laser part and the ice lithography part. I will start with ice lithography. So what is ice lithography? So first we need to revisit the traditional e-beam lithography. You need to have a resistor, and this involves rooms. And then you put them in vacuum to do exposure by electrons, and then you make patterns. And in order to have patterns to be really useful, you have to develop them. And then they are again in the chemical room. So you're taking out from vacuum into chemical room again. And then after develop, you need to do devices, and then involves, for example, material deposition. And this is again done in vacuum. And then in order to take away the resistors from the very beginning, you need to do liftoff. And this is again doing in the chemical rooms, involves chemicals. So chemical room, vacuum, chemical rooms, vacuum, and chemical rooms. So this is a very tedious and troublesome process. And we have been doing this for more than 10 years. And my students really tired of it because sometimes you need to take more than 2 weeks to make one device, and one step went wrong, everything went wrong. And then we start in collaboration with Harvard University and the Denmark Technical University, mostly Dr. Anpan Han, we are start to working on this ice lithography. So instead of using PMMA or ZEP and other resistor based on polymers, we start to use water vapors to condense them in very low temperature and make them as a very thin layer of ice, a few hundred or few tens of nanometers, and making the structure out of ice using electrons. And you can form structure directly. And then you don't need to take them out to the chemical rooms because the patterns, the structures are already made. You can directly put in the same vacuum, but with slightly different processing, deposit metals. And then you can simply, in the final stage, remove ice. And this can be done, for example, increase the temperature to the room temperature instead of very low temperature. And then you can easily make a very nice device without actually involved, at least not too much chemical rooms or chemicals. In our earlier days, we only need to involve one chemical room, chemical processing. All others are done in the vacuum, in one vacuum. So this is very easy to be done. And now I introduce the advantages of a water ice resistor. So why we think is interesting and important, because we can make a solvent-free nanofabrications. We don't need to deal with chemical process. And the chemicals sometimes will damage to many sensitive devices, for example, polymer devices, for example, perovskite, because they can easily react with chemicals. But if you use ice, there's no such a problem. And remember, actually, we are not really working with water, even they are water molecules. We are working with ice. But because we are working at very low temperature, so actually the ice directly moved to the gas phase. We do not involve any liquid phase in our process. It's basically a phase change between gas phase of the water molecules and the solid phase of the water molecules. And then they can make ice from water vapors from ice very easily. And the second advantage is because we evaporate ice on substrate, and ice is uniformly covers the surface of samples, whatever the shape is. So it's conformal coating of the films. But this is different from the traditional resistor. You need to do the spinning, and that can only, or not, at least not so easily to be done in the curved surface, but only on the planar surface. But actually, for example, we can do lots of things, including we can make a tiny titanium and gold tip on an AFM, and that's actually can be done. I will give an example later on ice lithography on fibers. And the third advantage is because we are making the water vapors directly in the vacuum and actually in an E-beam system. And when we making this ice, actually, if we carefully design the structure, we carefully utilize the E-beam lithography, we can look at the structure directly with ice. And then afterwards, we can increase the electrons, the intensity of electrons, and we start to remove part of ice. And then we can make patterns. And you can see from here, the darker part, actually here is the patterning we removed by removing ice. And this is very difficult to be done in the traditional resistors. You need to do lots of other things, including markers, And layer by layer fabrications usually takes weeks to have several layers. But for us, we can do it very easily. We can do in-situ alignment and correction. So based on these advantages, so at least my dream and my students' dream, and a very important person in my group is the Dr. Ding Zhao. And he's thinking of, instead of having such a troublesome and large area, large size clean room for nanofabrications, maybe we can move all these parts, whatever are they, into a single equipment. For even e-beam patterning and material depositions, we can connect them all together. And this is a design actually we came up many years ago, more than 5 years ago, and now we start to realize them. And this is the prototype and supported by a national project on these devices. And we can realize e-beam lithography, and we can do the sample transferring from the e-beam to material deposition in the same vacuum and easily. And so we are trying our best to realize a wafer-in device out, all-in-one nanofabrication e-beam, ICE e-beam lithography instrument. I think we have already achieved roughly 60% of our goal, and we are still working on this. So this is what we have already realized, part of them. And now we need to connect all these parts together and making an even more complete device. We still have a few years work to do. And give you a few examples before I move to the femtosecond laser part. So this is e-beam lithography. So we can only make small devices. Making very large device will be very expensive. So, but they do have tons of advantages, including, for example, and this is first example, a publication 2 years ago. We can pattern very special materials, including 2D materials. And we have actually tried several materials, including monolayer MOS2. And this materials is quite difficult to be done by nanofabrications. And we realized that actually, because they are very sensitive to electrons, because if you expose directly with electrons, you can take away them easily. And then combined with ICE lithography, we can either directly remove the MOS2 using e-beam or protect with ICE and then making ICE away, taking ICE away and then make electrodes on top of it and making connections and then making electronic devices. And this actually is already will be published soon in a very forthcoming papers, how to make an electronic device based on this using a combination of e-beam lithography plus ICE lithography. And another case is for the special materials is the perovskite, because we all know that the perovskite is very sensitive to the e-beam. So you can use e-beam to pattern the structures because they will have different photoluminance. And then we can again combine e-beam lithography together with ICE lithography, and then we can carefully control the photoluminances, PL, of such a special devices cases. And this is the first paper was come out last year, and we will have another paper coming out and how to make a very easy perovskite electronic device based on this. And for the details, probably that will be another talk. And this is another example of in-situ alignment and overlay. So, and to the right is our earlier work. We can make 3 stacking layers of device. For example, this one, a big square, a second layer of another metal, and third layer of third metal on top of it. And this is similar, and we can even make patterns, squares, circles. And at that time, I was still at Zhejiang University, so we make this the Qiushi eagle of the Zhejiang University on top of it. And this actually are all done in one single fabrication process. And we can also align this directly on top of another one. And so what we do is actually we locate a nanowire, a silver nanowire, and find under E-beam lithography, and then we directly deposit ice on top of it and remove part of the ice, and then deposit silver on top of it. And then we can align them properly, very actually in the tens of nanometers resolution, sometimes below 10 nanometers, and align them easily. Another third example is the optical fiber integrated device. So as we said, we can basically make E-beam lithography almost in any surface, as long as we can cool it down to a low temperature. Or I forgot to mention that by cold, low temperature, by cold ice, I meant something around 150 Kelvin, 130 to 150 Kelvin. So this is slightly above the nitrogen, liquid nitrogen temperature. So we can, by carefully design a stage, so we can make devices on the fiber end facets. And our method actually is quite easy. And we can not only make on end facet, we can also make on the surface of the fibers as shown in the earlier before. And this is, and we can even take away the ice using a simple blow-off process using nitrogen gas. And this is a paper we published 2 years ago. And finally, the fourth example I'm going to present is that we can even do 3D printing with organic ice. So that means if we use organic molecules instead of water molecules, like anisole, and then this is actually a liquid. And then if we make them evaporate and then condense again in a cold surface, and through our ice lithography process, we can make very complicated 3D structures. For example, this layer by layer structure. Actually, we can make almost any structure out of this. And we can also make them in any surface. And this is one of the example of a curved surface. So we can make this a very nice picture on top of this. So this is one of the examples I show here. So a logo of Westlake Universities, but colored. But unfortunately, this is only a size of a few tenths of micrometers. Actually, I have a sample in my hand. I don't know if you can say this. This is a sample made with Westlake logos, colored with Westlake logos using ice lithography. But it's too tiny to that the audience say. But this is one of the examples we can do. So ending the first 30 minutes, I'm going to move to the second part. So what we are thinking of fabrication is that we can do pretty good job with small devices using E-beam lithography. But we also have lots of applications. We want to have large very large surface, very large device, but still functional optoelectronics. So how we can do that? Is there any other alternative instead of electrons? So then, a few years ago, about 10 years ago, we started working on femtosecond laser. And in particular, for the last 3 years, we have some interesting results coming back. And now let's have the look. So femtosecond laser fabrication is already very common. There are lots of groups in the world are doing this kind of research. It has been around since the birth of laser, since 1960s. And in China, in the world, there are I think thousands of groups are working on laser fabrication and applications. And this including, for example, direct laser writings. So you can write laser on the hair or inside a fiber or any structures. You can even cutting the metals. You can also do lithography, actually. It's based on the interference lithography. So what you can do is you basically to put in 2 beams together, or 3 beams, or even more beams, and then you can make very uniform high throughput grating devices or structures. But robustness is an issue, of course, in this. And writing another problem is it's not so easy to writing a very large structures. And there's also another interesting thing is called laser-induced periodical surface structures, LIPS. So in this actually is the incoming laser light will interact with the surface wave generated at the surface of materials. When they interference with each other, it's possible to have periodical structures out of it. So it's very high throughput and low cost, but disadvantage is very obvious. It's not so easy to control, as you can see from here. So my group, there are 2 key persons working on this and generate lots of very nice and good results. And they are Dr. Li Pingsi, Si Liping, and Dr. Jiao Geng, Geng Jiao. So they have already working on this femtosecond laser fabrications for many years. So we have already started physics, techniques, engineering, and I will show you a few applications. And I will also show you some real examples using this method, in particular to do structural colors. So let's start with physics. So in our experiments, and this is a publication from last year in Light Advanced Manufacturing. So it's not really by accident, but almost by accident that we find out that under any surface of materials, you always have a small particle of oxide materials. For example, if you have silicon, you always have silicon dioxide nanoparticles because part of the silicon is oxidized by the surrounding air with oxygen. And actually, you can see lots of them smaller oxide particles. It's similar for aluminum or metal, copper, anything. So this is then why it's interesting, because we find out that actually if we have a laser beam shining on this, and they will generate a significant amount of scattering light. And if we look at in the same scale, we find out that, and this is not surprising, smaller nano particles have smaller scattering. then this is 100, 200, 300, 400, 500, 600. You can say that the intensity of the scatter light is become stronger and stronger, much more intense, used with larger structure. And then we find out that, okay, actually this is very interesting, because when we shine the light on top of it, this small oxidized nanoparticles will grow. And when they grow, actually, they grow in the same direction as the instant light, the polarization. So when the polarization is like this, so the light, this particle will grow to the up here and also here. So they will make a straight line. And then they will also, as you can see from here, when they grow on this end, they also will affect here and here. So that means after a very long structure, you will also grow a small thin line here, here, and then here, 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 growing. And then actually you will generate periodical structures. And this is actually exactly similar to these laser-induced periodical surface structures. And this, of course, the scattering is because you have a surface propagating wave. And this is how we grow them. So you can see from here. So by carefully control the polarization, we can basically make anything, because as I said earlier, that the growth of these things, these lines or the oxidized lines, are based on the polarization of the incident lasers. So if we have like circular polarized light, actually they will grow like this. And if we have very complicated different kind of polarization by polarization control, and we can make lots of beautiful gratings. And you can also see from the optical image, they also give you shining rainbow colors. And actually, that's something I will show you later, and this basically inspired us to making structural colors out of it. And I said, and again, so this is a video I'm going to show you to see how these gratings will be formed. And in this case, actually, we do not need to, in the traditional ways, we need to write these gratings by scan the laser along these lines. But you see from here that we shine a very large, like this size, in a diameters of a few hundred micrometers, and such a very broad laser beam. And then you can see the grating will automatically create it. And the reason why you have several parts of this grating is because it might happen that there are several larger seeds or larger nanoparticles, and they all compete with each other, but eventually they will merge. And the reason why they merge to be a quite similar ones is that as long as we control the polarization, in this case, the polarization is parallel here, like this. So no matter how they grow, they will always grow along these lines. And this is why the reason why they will grow. Let me show you again that they grow to a very large and beautiful, precise, almost precisely controlled gratings. And all these gratings have a period similar to the incident wave. So we are using 1030 nanometer wavelength femtosecond laser. And then the period actually here is around 900 to 1000 nanometers, depends on the thickness of the substrate. Oh, I forgot to mention that in this case, we we in particular glow these gratings on a very thin layer of silicon on top of oxide. And this silicon is in order of tens of a few hundred nanometers. So it's basically oxidized silicon dioxide. But on the other hand, when you see from here that they are not really so beautifully processed because you have several nanoparticles, and even they merge. And when you still see that at the area of the merging part, the grating period are not so good. So Dr. Shi Liping and Dr. Geng Jiao, they are thinking, okay, what kind of technique we can have a very beautiful, large size gratings. And we can write them, these gratings, in few seconds for a whole wafer. And they came up with this idea, artificial seeds. So we have been discussing actually within group for many months how we can do this. And then one day I said, okay, why don't we design a special seeds on this? And this is one of the very recent publication will actually appear in this and photonics review shortly, is that we use two lasers in this case. Instead of not only an femtosecond laser with these parameters, 5 kilohertz repetition, 330 femtosecond, 1030 nanometers. We also have another half wavelength. Actually, it's based on nonlinear effects. We also generate short wavelengths, 515 nanometers. And we use this to write special seeds. Actually, write is a tricky word. What we meant here is actually to use this laser to induce the oxidation of silicon. Again, we use a silicon on top of metal substrate. So this is a comparison. This is actually is a series. So if we have lots of small particles, as we have seen in the previous videos, so they will all scatter, and then they will generate lots of strange patterns. But if we have lines like this, as very thin lines, length of a few hundred micrometers, so the scattering wave will be very regular. And since they are very long and large lines, the scattering intensity is much larger than the scattering from these small particles. So these smaller particles will not be affected. These gratings will still propagate. And of course, when we truly prepare the samples, we will try our best to remove these nanoparticles. And of course, you cannot remove all of them. So use this direct laser writing to make an artificial seed. And base this artificial seed, and we can start to make gratings easily. And this is what we can show you how we can do. And to the left is without seeds. We can still do large area gratings, but they are not so regular. But if we have a more than 100 micrometers seed be written first, and the generate grating is unbelievably beautiful. And this is what we can do. We can even make a special seed like this, the curved lines, and then we can make a curved gratings. And again, we can make them very easily. So we solved a lot of problems using this technique. And then we start to apply this method to make extremely large and high precision nanogratings. So, and I give one example. And this is another paper we published very recently in Light. So make a seed and write them in a rapid way. So this is the seed, and in this case, we are also making silicon on either copper and silver surface. We want to see the difference. Actually, there's no much difference. But the wavelength, actually, the absorption wavelength is around this. And actually, this is coincide with the grating period very well. So this is the results I want to show you. So very high speed, because this is 2-inch wafer. And we write the whole 2-inch wafer within 20 seconds. And then it's very robust. And since we can do it very fast, of course, it's low cost. And we don't need any mask. So this is a grating of period error below 0.5 for the whole 2-inch wafer. And it's also extremely energy efficient. And we can achieve very high speed, but with extremely low energy as compared to others. So if you're interested, you can look at details from this paper. And with these wonderful gratings, we can do many applications. For example, you can make the surface to be a sensor. So I give one example. And this grating naturally have a Q value of a few tens. And you can utilize these gratings making a resonance and using this resonance to detect different liquids. And we found out that it's quite high figure of merit refractive index, because for both these two resonators, we find out they are either the sensitivity is either 360 or 650 nanometer per RIU. I wouldn't say they are very the best sensor, but they are very cheap to make. As I said, we can make them in 20 seconds in a 2-inch wafer. So it's only minutes for 4-inch wafers. We have already done that. And then another thing we are trying to do is we can make these beautiful gratings, and they also have very shining colors. But these colors, we realize that actually they are angle dependent. That means if you look from the different place, different angles of wafers, that means if you have a wafer like this, so if you look at the different angles, they will be different. And then how to make the different things carefully. So very recently, we came up with ideas of English color printers. And by structural colors, there are many ways to make structural colors. So you can do it with nanogratings, as we have already shown here, but it's viewing angle dependent. It also have quite low resolution because you cannot control the small spot. You can also making a fibroprobe cavities based on resonance, but it's not so easy to have a low cost. And metal surface, either dielectric and metallic, can also be done because you can make beautiful nanostructures and you can make any color out of it. But it's very low efficient because we have been working with ISIS lithography and many e-beam lithography methods for years. They're truly difficult to do and efficiency. So my request, and when we discuss with Dr. Shi Liping and Dr. Geng Jiu, is it there a way or platform we can play, and then we can make very large structures with structural color. And then we came out that actually multi-layer structures, films, is possible, even though for the time being, they still have viewing angle dependent and low resolution problems. So we need to solve this. So how to solve this? We find out that it's possible to solve this with structural color. And then we need to find a platform to play with. And we need to design a very special multi-layer films. And they have to, and since we want to make a painting out of it, so they have to be angle robust. So it should be angle independent when you see different colors. It also should be wear resistant. So I cannot afford some beautiful pictures painted by $1,000 or even $10,000 using nanofabrication, but you cannot even scratch it like this one. And we find out actually there's a very interesting platform, is titanium aluminum nitride or titanium nitride. If we make them multi-layers, actually they can survive at a very high temperature, and they are very wear resistant. And this is a silicon. You can easily scratch them, but for titanium aluminum oxide, it's almost impossible to scratch them easily. And then they also having different beautiful colors. And these colors are also angular independent. So now we try to say, okay, we have a good platform. And then we use femtosecond laser to make colors. And with different design of films, and we find out that it's possible almost cover all the colors. And most of the structural color existing ones, they can only cover 10 to 20% of the sRGB color space. And we think with these material systems, when we design the film carefully, and we can actually almost cover all colors, including black and white, and red, green, blue, yellow, almost anything. So you can see from here, it covers almost the whole space, about 90%. And this is due to the double resonance. And they are very thin layers. Even it's multi-layers, we can make them only roughly 50 nanometers. So with such a thin film, they are angle robust. So at least viewing from 0 degree to 60 degree, the color does not change significantly. And this is an example we show, and I will show you in the end of the part of the talk. And if you are interested, you can download our very recently posted archive paper. And we can make very beautiful colors and beautiful pictures in a wafer scale. And this is a 4-inch wafer. And we make a very nice Ming Dynasty painting, part of it. And for the Chinese audience, you may know that is actually my ancestor, a famous painter called Qiu Ying of Ming Dynasty, and shared the same family name as mine. He painted. It's called the life in a palace, Hangong Cun Xiao Tu. And this is part of, you can see the beautiful colors and also the resolution. We can actually achieve resolution of 250,000. It's almost close to the diffraction limits, because the only thing we need to do is how to make a very small laser beam. And you can also see the color. And this is the Weeping Woman from Picasso. And the left one is the original one. And this is our replica using the laser painting. You can see the color. I wouldn't say completely the same, but it almost reproduce all the colors. And you can also making, I'm a fan of Chinese calligraphy. So I also love this very beautiful writings, 兰亭, Xu from 1,500 years ago by Wang Xizhi. And we make a colored version out of it. So, and it's difficult to show you in the presentation, because I realized that only this online presentation, it's difficult to see the true color because it's in the evening. I don't have very nice lighting. Probably I need to improve in future. But this is the weeping woman. And this is the Han Gong Cun Xiao Tu from the right. And I also have a wonderful Lan Ting Xu. And this Lan Ting Xu is made on the steel foil. So it's very thin, very thin. So you can even fold them on a can very easily, but with very nice color. So this also tells you a wonderful applications. And at Westlake University, so we very recently we start to admit our undergraduate students starting from this year. And from this year, actually the first cohort of undergraduate students for Westlake University, and they receive a present from my laboratory. So we give them a 2-inch wafer painted with the part of the campus of the Westlake University. Actually, this is academic ring on this. And then on the back side, I don't know if you can say, but on the back side with the name of students. And in this sample, actually, it's the name of our president, Shi Yigong. And again, it's colored. But unfortunately, it's in the evening, it's not so easy to see the beautiful colors. But this is a picture, a real picture taken by our photographer. So, and another thing I want to show you that, as I said, and they are extremely wear resistant. And this color is different from any paintings you see in other places, because for usual painting, you cannot really scratch them. You cannot touch them because it will destroy the color easily. And with this one, actually, we can use pen to write on top of it. This will not, for example, with my fingers, it will not give you any problems to the colors or to the structures. And it also high temperature resistant. So most of painting, we all know that if we burn it with lighter, they will disappear. But I don't know if you can see from here, but let me carefully do it. I can even using this high temperature to burn this. I don't know if you can see easily, but hopefully you can do it. So you can see, and this is, I cannot even touch this silicon wafer. It's already a few hundred Celsius degrees. I can even smell the I can even feel the high temperature, but you can see here, the color is not changed. And they're also very fast because this is the last video I'm going to show. So Professor Ma, don't worry. I think I still have 2 or 3 minutes since we start at 8:04. So, sorry. Wait. Oh, sorry. So this is how fast the painting. So they are writing the name of my laboratory. So we can write these characters in few seconds. So the whole picture of the above one can be done in a few minutes or few tens of minutes, depends on the resolution, of course. If you really want to have an extremely high resolution, like 250,000 dpi, that will take many hours. But if it's only printing resolution like 360 dpi or 720 dpi, that's the regular laser printing resolution. That's only a few minutes. You can make a very nice, colorful pictures, which you can preserve for hundreds of years because they are extremely resistant to high temperature, to chemicals, to scratch, or almost to anything. And they also cover almost all the colors. So finally, I will say a few words. We have been working on nanofabrication technologies for years, for more than 20 years. And we see lots of challenge and opportunities. And the painting, like this one, is one of the possible applications, of course, but it's very close to everyone's life. And we are trying to find a way to commercialize it. But we still need to find out what kind of things we can do in future. For example, how to, in the material level or fabrication level, how to get better property, high quality, fewer defects, and large size of nanostructures on any materials. And this is extremely difficult. And we achieved some part of it, but we still cannot do everything. And on the technology side, how to jump out of existing framework, the e-beam lithography or the CMOS technology, silicon technology, but think of new lines of effectively integrate photonic and electronic devices together in one platform, in the hybrid platform. And even in the characterization, how to obtain optical, electrical, and mechanical, and other performance of a device in-situ easily. And this is still an open question. I would say we only, in my group, we just a beginner. We just solved part of it, but we see lots of interesting things can be shared with others. So that's all the things I want to share with you. Thank you very much. And I also look forward to the discussions after the presentation. Thank you very much.
Thank you, Professor Chu. Thank you for the wonderful talk. The technology and the results you presented are really highly impressive. Thank you. So I think before we move to our panel discussion, please let me first introduce our panelists and the ex-challenger. So we have two panelists tonight. The first panelist is Professor Li Wei. Professor Wei Li is a full professor at the Changchun Institute of Optics, Fine Mechanics and Physics. Professor Li Wei did his PhD and postdoc at Vanderbilt University and Stanford University. His research interests include nanophotonics, thermal radiation, and their applications in next generation energy and information technologies. His work has been published in Nature Photonics, Nature Nanotechnology, Nature Communications, Nature Review Materials, and Light Science and Applications. He has been granted with the key program of the National Natural Science Foundation of China, multiple Young Investigator Programs, and the Mine Young Scientist Award. Here is our second panelist, Professor Rong Chen from Huazhong University of Science. Dr. Chen is a full professor at Huazhong University of Science and Technology. She is the Associate Director of a Flexible Electronic Research Center at Huazhong University of Science and Technology. Professor Chen received her master and PhD degree from Stanford and a bachelor degree from University of Science and Technology of China. She was a senior research scientist at Intel Labs before she joined Huazhong University of Science and Technology. Her research focuses on atomic level manufacturing, sustainable energy, semiconductor processing, and technology. Professor Chen has published more than 130 peer-reviewed journal articles. She has been granted more than 70 patents and jointly published 4 books and book chapters. She has given more than 40 plenary keynote and invited talks and served as the editor for a number of prestigious journals. Professor Chen has received Innovation China Leading Technology Award, IEEE SMC 2020 Distinguished Academic Contribution Award, the first prize of technology invention in Hubei Province, the Hubei Province Intellectual Property Award, the Special Golden Prize of Geneva International Inventions, and a number of other national and international prestigious awards. Let's welcome our 2 panelists. We also have our ex-challenger, Dr. Julia Chang from Fudan University. Dr. Julia Chang received her PhD degree from Iowa State University in 2020. She is now a postdoc at Fudan University. Her research focuses on semiconductor nanomaterials, functional materials based on liquid metal and metal surfaces. She has published 4 papers and 1 patent. She received the Best Poster Award in the MRS 2017 fall meeting, and her work was reported by Forbes magazine. So let's welcome our panelists and ex-challenger, and of course our invited speaker, Professor Ming Chiu. So for starting of the panel discussion, we will have our ex-challenger, Julia, to ask questions. Please, Julia.
I think you are muted. Yes.
Oh, yeah. Sorry. I want to thank Professor Chiu for the beautiful talk and the presentation. And I actually have 2 questions for you. The first one is about the ice lithography. As you have demonstrated, the ice is actually used as a photoresist for the e-beam lithography. And actually, the water ice is a positive resist, and the organic ice is a negative one. But the pattern is still generated by the e-beam lithography. As we all know, the crystallization of ice itself could be a very ordered process, and it will form some very ordered structure like the snowflakes. So my question is, could we use this ordered crystallization of the water to form some ordered ice structure as both the resist and the pattern for the lithographies? Professor Chiu.
Oh, thank you, Julia. Very, very good question. A wonderful question. You are absolutely right. Well, we have actually, in the beginning of years, we start ice lithography research about 10 years ago, 2012. It took us 3 years to make a nice pattern in a very out of ice. The reason is it's very difficult to control ice. Water has roughly 19, if I remember correctly, different forms of solid forms. So even with ice, they have 90 different forms, including the structure similar to snowflake. And this is more close to a crystal, water crystal. And this is at a low temperature, but not so low temperature. It's close to just a little bit below 0 degree of Celsius degree. So roughly 273 Kelvin. And then when you reduce the temperature to a lower ones, you will have different phase of ice. And what we are working at, the reason why we work at around 150 Kelvin is that at that range of temperature, ice is basically amorphous ice. So they will not become water crystals. And then it's actually a tiny, small clusters of water molecules. They are stacking with each other. And at this amorphous phase of the water molecules, but again, still crystal, not crystal, still solid. And they will interact with electrons easily. They will absorb electrons and they will become heated a little bit. And sometimes not only heated, but the hydrogen will deassociate from water molecules and they will evaporate. So this is the process. And so we have also tried, as you suggest, for example, starting from a higher temperature. What I meant high here is still below 0. It's below the condensation of water molecules, the temperature. And then it will become very difficult for us to remove ice because the water crystals, the water molecules, they stick to each other much more as compared to the amorphous ice. So it's very difficult for us to do that. But what you said is still interesting. So we will say, if, for example, if we start with a little bit higher temperature to form a special structure first, and then to a lower temperature to see if it's possible to do patterning on top of it. And this is something we will look in future. But according to our experience, there's very tiny snowflakes is not so easy to obtain. At a little bit below 0 degree of Celsius temperature, the size of the snowflake are in tens of micrometers, sometimes in millimeter or centimeter. So it's not so easy to reduce them to micrometer or nanometer. Actually, we made one of this world's smallest snowflake out of ice lithography with the size of micrometers. So I don't know if it's possible to merge these two words. But definitely this is a very interesting trend or very interesting direction we can look in the future. Yeah, thank you.
Okay, thank you. There is a lot of experience talk, and I think it's really helpful. And I got a second question. It's about the laser work. As I understand, and please correct me if I'm wrong, the seed you created, actually it's a structural seed. And I think yes, it's a really, really smart design. And I guess the metal layer is actually a pretty important part of the whole design because it is the actual carrier of the surface plasmon polariton that will heat up the adjacent region and create all these kind of lines. So my question is, could we just replace the silicon layer with ice? Then we could combine the ice and the laser lithography together, because we all know that E-beam cannot compare with the laser in the efficiency part. So this is my second question.
Yeah, it looks like you read my brain, basically. read my mind. Actually, this is one of the things we are trying. Actually, it's still ongoing, because it's not so easy to introduce the laser into the e-beam lithography chamber because the space is very limited. But we are trying to do that. That's possible. Actually, what you said at the very beginning is correct. So the underneath metal is important because you need to generate a surface plasma wave. So it's interference with the incident laser light with the surface plasma wave. So this interference is the most important element to generate a large scale and gratings. And that's another reason why it can be so fast, because surface plasma wave can propagate for few tens, even few hundreds of micrometers, while cylindrical wave cannot do that. So that's why it's so fast. But for eyes, I'm not so sure, but we will definitely try it. Actually, one of the work Dr. Zhao Ding is trying to do is they're collaborating with Shi Liping and Joyce to see if it's possible to introduce the laser into the e-beam lithography chamber. I don't know how long it will take, but because that involves modification of e-beam lithography, and it's a $1 million equipment, and so we do it very carefully. But hopefully in 1 or 2 years we will give you some interesting results, and that's exactly what we are doing right now. But anyway, thank you for the question and thank you for the suggestion.
Thank you, Professor Cho. That's all my questions, Professor Ma.
Thank you.
Thank you, Julia, for the wonderful question. And I enjoyed very much your question and the discussion from Professor Chiu. Okay, so how about our panelists?
Well, maybe I can start.
Sure.
Professor Chiu, thank you so much for your fascinating talk. I greatly enjoyed and learned a lot. It's very fascinating to see your ambitious plan of wafer in, device out, this plan, and as well as to see how you really push the structural color to a completely different level. So thank you very much. I guess I have multiple questions. The first one is you in your talk you show like two interesting fabrication techniques. The electron beam based technique have a very good precision, but limited to a small size. The laser based approach, you show a very impressive speed, like you show 2-inch wafer within 20 seconds. But the feature size, I guess in the end is limited by how the surface wave effective wavelengths. Exactly. So in the length level of few hundred nanometers. So moving forward, as an expert in this field, I'm curious, like, what's your view as a promising approach or direction that can produce large area fabrication, but with a high precision?
Yeah, very good question. So what we are doing right now is, in my group, there are several things. First is exactly what Julia just suggested. What we have been doing for some time is combining the e-beam lithography with laser fabrication. So try to combine these two words, merge these two words into one. And that's one trend, one possibility. Another possibility is to break the diffraction limit of laser processing. And we have already tried recently on making sub-wavelength gratings using similar technology. But this is fairly difficult. Where, as you are correct, for 1030 nanometer, we can only make the grating of period roughly 800 to 900. And this is because of the surface refractive index limited. And we are moving towards below 500 nanometer, and hopefully we can reach below 400 nanometer. Then we can cover the whole visible light range. But this is I don't know, but this is another challenge to combine the third word. So basically how to break the diffraction limits with lasers. And there are lots of nonlinear effects we need to utilize. Fortunately, femtosecond laser, they have high energy, high power intensity, so it's possible. But that's something we can do.
Okay, great. Thank you so much. Maybe I have another question. Maybe that's beyond this talk. I'm asking for myself and also my team members. That is regarding to the time management. I know that you are leading Westlake University and leading a big research group, and yourself is also a marathon runner. So apparently you are doing multiple things and many great things within the similar time as others. So just curious, like how you do the time management, and is there any special tips for us, like for young scientists and the students?
Yeah, this is again good question. It's not so easy to manage time. So what I do at least for my past more than 20 years of research, how to balance life with research, and also, as you said, I'm also heavily involved in the administration of a new university. So what I do is to always pick up. First is always pick up important things. So for tomorrow, you always have like 10 things to do. So you have to pick, or you probably need to list them and to say what are the important things. You have to be sure. And the second thing is try to arrange your schedule wisely, and also with the help of your colleague. You cannot do everything by yourself. So for research, most of my work present earlier are done by my co-workers, Dr. Zhou, Dr. Shi, and Dr. Ge. What I need to do is I need to spend lots of time to discuss with them, to work with them, and to read papers or writing manuscript together with them. And then it's again, so most of administration time is happening roughly between 8:30 to 5:30. And in the evening, it's just like this tonight. I spend most of my time on research. And actually, I also have family, so I spend most of the time at home with my kids and also with my wife, but lots of online talks and such meetings with my coworkers. But again, I don't think it's not so easy. So, and in the morning, I also run, not every day, but almost every 2 days, 10 kilometers. And this is another thing I think important for me, because it can keep the energy from my body, basically. I know some of you are also running. Professor Ma also a very wonderful runner. So to conclude, I think is to try to realize what are the important things you want to do in your life and in your research. Even for the administration or research, you cannot do everything. Pick those important ones.
Okay, thank you so much.
Okay.
Okay, Professor. Yeah, go ahead.
Professor Cho, thank you very much for your wonderful talk, and also give us some great ideas on how you do the time management. I especially interested in your talk since I think it's full of science as well as the arts. Especially I think for the ice lithography, to me it's quite inspiring because I'm mostly working on this kind of semiconductor type of lithography. So to think of the ice, I think it's environmentally benign compared with all this kind of polymers, because we generate a lot of solvents, a lot of polymers during the lithography, the spin-on processes. So I'm wondering whether you could comment on ice or this kind of cryogenic compounds. Consider all of them are small molecules. They're smaller size compared with polymers. So I'm wondering how is its future towards this kind of very, very small scale lithography, such as EUVs. Are you already use, because you already use the electron beams? I'm just wondering how small it might get into in the futures. That's my first question. Thank you.
Yeah, it's a very good question. So one of the reasons why we work with water molecules is the smaller size, as you point out. So in principle, the resolution can be very high because one water molecule is basically only 0.1 nanometer. So if we can remove one more water molecule by one, so that means the minimum size you can do is 0.1 nanometer. But this is very difficult. We cannot really realize this in our lab yet. One of the problems coming from our lab is actually the vibration from the neighboring labs, from anywhere, from the road, cars. So this is something which we need to solve, actually. So when you come to the high resolution, there are lots of things to be solved. As you said, it's more or less like art. It's not only small molecules or E-beam, it's also mechanical engineering, how to remove vibrations, how to stabilize the temperature, for example. If you have unstable temperature with the cryogenic stage, it also gives you different problems. So there are lots of things to be solved. I don't know if there's a very bright future for ice lithography, but to me and to my group, for example, to Dr. Zhou, and also we have 5 PhD students working on this. To them, it's fun. It's very interesting because they are working something different from others. I also get some comments that, oh, yeah, you're working with ice lithography, but what's the use for semiconductor industry? I said, I don't know, but I can do something very interesting. For example, I give you one example. One of my students very recently applied ice lithography to a living small creatures. Actually, it's a small, very small, tiny worms. I cannot tell you exactly what it is because we didn't publish it, but only size of micrometers, and we can make a small, you can say nanostructures or nanophotonic device on top of this living creatures. We can froze the creature and do the nanofabrication and then bring its life back. So this is something I don't think you can do with any other nanofabrication technology. And it's still at the early stage. So who knows? So that would be something fun. That's the beautiful part of research.
Yeah.
Not all science will be useful, but it could be fun. That's already enough.
Yeah, I think that's actually quite great because just as you mentioned, I never really thought of, I mean, this one could be applied to living animals or whatever, living things. Yeah, that's really interesting. So my second question is for the laser work, because I think you generate tons of this kind of structural colors in such a quick way. That's quite impressive. And I also noticed that on your slides, you mentioned that you may want to push to the AR, VR type of applications. So compare with the nano imprint, because we know sometimes people right now use nano imprint. I think your method is also generate all these kind of micro nano structures beautifully. So could you also give us some comments on that?
Yeah, this is also interesting because it's truly related to my group's work, because I only present part of this, and I also have a small part of my group working on how to generate structures for AR and VR. And nano imprint is so far is the best way to mass reproduce these structures. But you still need to have a mold to make nano imprint, right?
Yes.
And making this mold is not so easy. So actually, our task is to make this mold. And if I understand correctly, and at least to my knowledge, there are only 2 companies in the world can make this mold for mass production. I wouldn't say for lab use, but at least for mass production, there are only 2 labs in the world can do beautifully this. And at least we are trying to be the 3rd one.
Wow, that's great. Yeah, thank you very much. I think you give us the science, arts, as well as your views on how it could impact for our lives. Thank you very much. Dr. Ma, I'm finished my questions. Thank you.
Thank you, Professor, for the wonderful discussion. So I myself also have some questions, but for the limited time, I think I will save my question for future offline discussion with Professor. So to give the chance to our online audience, they have also a lot of questions. So the first question is from I can ask the founder, Professor Zhang, Alice Zhang. So she want to ask, she said, Professor Chiu, thanks for your wonderful talk. Amazing results. I have a question about your all-in-one fabrication of eyes. Did you use it to fabricate medical devices for drug delivery? I think it has a special advantage in this area.
We are thinking of it, but we don't have the expertise on the drug delivery. And actually, I was discussing with one of my students, and actually who graduated now working at Huawei. And we are thinking of using eyes to make, for example, to optofluidic devices or some other devices to deliver drugs. But we didn't really go further is that we don't have collaborators on this. So I really welcome Alice or any one of you who have expertise on drug delivery, and we can help. We can basically make, I wouldn't say any structure, but at least very nice structures on almost any surface or any structure. So I also really look forward to it.
Okay, thank you.
Collaborations.
Thank you. So there's another question from An Yang from CIOMT. He said, thanks for the great talk. Is this femtosecond laser inking angle independent? If yes, what is the reason for titanium nitride independent of angles?
Okay, yeah, this is a good question. I can, for the details, you can read our archive paper, but I can explain this in a very simple way. Actually, this material is a lossy dielectric materials sandwiched with metal devices. So it's lossy materials. And the loss will give you extra phase change when the light propagates in films. And Renmin, Li Wei, you are all the expert on this, so you know this. So with the help of this extra phase change, you can easily achieve the phase required for the color change, for the resonance, basically. But we see a very thin layer of the films. And if the layer is thin enough, it will be angular independent because the phase is coming from the absorption instead of propagation. There's also shortcome, disadvantage coming out of these films is light will be lossy. So our colored structure looks a little bit darker as compared to other printed device. So we are working on this. And actually, in order to improve this, the best way is to reduce the thickness of the film. We have 50 nanometer, roughly 50 nanometer. If we can reduce to 20 nanometer, the brightness will be increased at least twice or even more. So that will be helpful. And with even thinner films, the angular independence will be even better.
Great, thank you. We also have a question from Germany. That is from Peilong Ho from University of Freiburg.
Mm-hmm.
He said, "Dear Professor Chiu, thanks a lot for your so insightful talk. I'm new to e-beam lithography, and I want to know what during the e-beam lithography process or ice lithography process, will the electron beam destroy the substrates underneath of the resistor or ice layer?" Have a nice weekend.
Okay, yeah, it depends. So it depends on what kind of substrate. For example, if you have 2D materials in our experiments or perovskite, if you have electron directly intact with this substrate, they will truly destroy the substrate. So in this case, ice will be a protecting layer for e-beam lithography. On the other hand, electrons can penetrate into ice fairly easily, depends on the energy. So we have a study a few years ago on how the ice will interact with electrons. But there's still something remaining to be investigated, is what happened when electrons interact with water molecules. And we find that, I think as I explained earlier to Julia, that there are two processes. One is they will be heated. When they heat it, they will evaporate water molecules. Others, when the water molecules absorb electrons, actually the hydrogen will become, will also disappear, will be dissociated from the water molecules. But what percentage and how they dependent on the electrons, we don't know. So it's not so easy for me to answer this question. But I can only say that it depends on the substrate, sometimes even depends on the experience.
Okay, thank you. Another question. Thank you for your excellent talk, Professor Chiu. I am Wei-Tong Lu from BIT. I want to know, how do you control the flatness of the edges when you're doing ice lithography?
That's also a good question. So the surface roughness first is very low, because as long as you control the temperature carefully, and when you move to the amorphous phase, so the surface roughness is only a few nanometers, because it's roughly a very few layer of water molecules. While the edge roughness is a tricky issue. It depends on lots of things. But according to our experience, if we can control the vibration, environmental vibration properly, we can have very beautiful sidewall roughness. We can easily make a very high aspect ratio change out of this ice. So for example, we can make 30 nanometer gap in 600 micrometer thick ice. So it's already 20:1 aspect ratio. So the roughness is not a big problem as long as we have a beautiful control of the electron, energy of the electron, because they are taking away more water molecules. This is different from the chemical reaction happening in, for example, PMMA or other E-beam resistor.
Great. I mean, the talk from Professor Chiu is so wonderful and inspires so many questions. But I get the instruction that we can only have one more due to the time. So let's have the last question. It is from Li Jiacheng from UESTC. He said, Professor Chiu, thanks for your sharing. I am wondering that can these proposed nanofabrication techniques have the ability for enabling meta lenses in the application of DUV lithography? If cannot, why? Thank you.
Well, I prefer to say it can, because that's one of the things we are working. Many of you know that I have been working in the metal surface area for some years, actually we didn't work on this device too much, on metal lens too much, is because we find out it's not so easy to fabricate them. So ice lithography we have tried, but unfortunately it's too slow. You cannot make very large structure. So laser-based nanofabrication is possible. Actually, the structural color, the method we make a structural color is a method we are trying right now to make a large scale, large surface, large area metal lens. But it's too early for us to say anything right now.
Okay,
but,
great.
But I think it's possible.
Okay, great. We will expect your wonderful news in the future. Great, thank you. Thank you, Professor Chiu, and also thank our panelists, Professor Chen and Professor Li. Also thank our ex-challenger, Julia. Wonderful discussions. Okay, great. So now let's move on. We will give the certification to Professor Chiu for the wonderful talk at the ICANN-X Talks.
Thank you very much.
Thank you again. So here is the next ICANN-X talk. Next week, we will have our speaker, Oscar Martinez from Argentina. Alex told me that this is the first talk from South America. So let's expect it. The title of the talk is Suppose You Can See Beyond the Diffraction Limit and Just Processing a Standard Image. Okay, that's all of the ICANN-X talk tonight. See you next Friday. Thank you all.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的人旁。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限。